Hello, we are Group 39 and this is our glider project. We designed and constructed a small glider capable of flying 20 feet. We were expected to use research and knowledge learned from class to build a functioning and successful glider. The design requirements are: the glider must be hand-thrown, it must fit in a 16 by 16 inch box, it must remain intact through flight, no post-throw control of the glider is allowed, no built-in propulsion system is allowed, and the glider must be mainly made with the balsa wood provided. We had 3 design alternatives. All had a dihedral angle of 5 degrees and were the max size possible. They had different wing shapes and stabilizer shapes as well as manufacturing methods. Design 1 is relatively easy to manufacture, but the mixed elliptical wing shape causes unnecessary difficulty and risk. Design 2 has similar pros, but includes more difficult parts, and the wings are fully elliptical, making it even harder to cut. Design 3 is the easiest to manufacture, but the slits may cause an uneven wing angle if done incorrectly. Design 1 was our initial prototype, which failed due to stalling. Thus, after many modifications, we created Design 3, which was easier to build, had more wing stability, and much better distribution of weight. Our research indicated an ideal glider has an aspect ratio between 4 and 8, a greater wingspan than fuselage length, and maximal area.
When designing our prototype, we had to consider many factors. For our wing and stabilizer shape, we went with a mixed trapezoidal and elliptical shape because that would give us the combined benefits of reduced drag while also being easier to create. We used a 5-degree dihedral angle because all of our research suggested that gliders will generate more lift that way. We considered using 3D printing PLA material for the prototype, but ended up using styrofoam and cardboard because it's lighter. We cannot use our balsa wood because we needed to save it for our final design. Our research led us to place the wings about 1/3 length of the fuselage behind the front for ideal center of gravity. We placed the tail flush with the back for ease of manufacturing. Research suggested that a cambered airfoil would be best, but because our balsa wood wing was too thin to shape, we left it as it was. We built and tested our prototype design, and it was relatively unsuccessful. During flight, it flipped backwards, meaning the center of gravity was too far back and the glider was unstable. Overall, it reached 12 feet, which was just over halfway of our minimum goal, so we needed to make modifications. The prototype did satisfy all requirements except for remaining intact, and it didn't reach 20 feet. The materials requirement was negligible for the prototype because we saved our wood for the final design anyway. To improve our glider, we reconsidered some of the design aspects. For the wing and stabilizer shape, we made them just trapezoidal because the curve was giving us no real benefit. We kept the same 5-degree dihedral angle because there was no reason to change it. To make it more effective, though, we cut slits along the fuselage so that the wings would not move. The prototype's material caused a lot of weight issues, but we had planned on using balsa wood for this final design anyway, so that's what we did. The wing and tail placement along the fuselage did not need to be changed. To adjust the center of gravity, we would just use Play-Doh. We also did not change the airfoil because, again, we didn't really have any room to work with. The final design is essentially the same as Design 3 from our design alternatives. It's a combination of all the modifications we made. It ended up having a center of gravity about half a centimeter back from the 1/4 chord spot. On the right is a picture of our final glider. We measured things like glider mass, planform area, and wingspan, and used these numbers to calculate our lift and drag coefficients. The calculations are in the images below. The lift coefficient was about 0.06 rounded, and the drag coefficient was about 0.0006, also rounded.
Through the prototype, we learned that we needed a more secure wing attachment method than just glue, that our wing shape had very little impact on the performance, and the importance of the center of gravity.
After some minor adjustments to the mass and placement of the Play-Doh, we had the glider consistently flying 80 feet or more. This is a video of one of our best test flights. In the video, the glider flew 80 feet and it was very stable in its whole flight.
The design not only met every requirement, but it also surpassed the goal by over 400%. Glider successfully achieved all requirements of the project. Using balsa wood, trapezoidal wings, and Play-Doh, we achieved a stable and lightweight design. Throughout the test flights, several areas of improvement such as functional design, efficient manufacturing, and stability provided the iterations that we made in the final design. This included fuselage incisions, trapezoidal wings for manufacturing convenience, and Play-Doh weight distribution adjusting the CG. Some improvements that could have been made are a more permanent weight distribution, better aerodynamics, and a true lift creating airfoil. These are the references for our research. Thank you for watching.